Welcome. In this session in linear data analysis, we'll explore a couple of examples of data that we can use for linear regression. One example are data that appear to be in a 1D vector space. That is, they go through the origin and they appear to be linear. And one person who discovered a rule for this was the famous 17th century intellectual from England, Robert Hooke. Hooke was an amazing person. He was the first person to discover a microorganism using a microscope. He surveyed half of London after the Great Fire. He was a professor of geometry. It's just astonishing. And data that follow a line that go through the origin is referred to sometimes as following Hooke's law. So here, what we have, we can imagine that this is our A, our independent value, and these are, let's say if in Hooke's law, it was for a linear spring, and we can represent A as being how far the spring was pulled or pushed from its neutral position. And this value, which we'll represent as C, in a spring would be the force. So it would be the extension or compression force that the spring exerts. So now, let's develop a mathematical model for Hooke's law and see where it takes us. One model that we can use is a pattern that has a constant slope. And this would model our data as being a scalar multiple of the observation. And in Hooke's law, this would be the spring constant that associates the extension or compression with the force that is exerted by the spring on an object. In our case, the residual model for the ith observation would be the ith extension of the spring times the spring constant. This is our model, and then we take the difference between the observed force and the modeled force, and that would be our error. The normal equation of projection is something that we've gone through in a previous session. We were looking then at taking a vector C, which in our case is all the dependent observations gathered together into a vector, and the independent observations A, also all gathered together in a vector. And when we do that, we can find this scalar W, which is the parameter of our model, by taking the ratio of two dot products. Now suppose that we have data that appear to be one-dimensional, but there's an intercept term. And our data might look like this. We can see that there's a seemingly linear relationship between the data, but it's not a vector space because this is the origin and the data are offset from the vector space. That means that our model of the data has to include an intercept term. Now, let's work through this intercept term by hand. For that data that we just examined, the model is a first order polynomial. And that means that for a given observation, using now we need more than one parameter, we'll say that this is W1 times our observation with an intercept term of W2. And the approximation that we are looking at is, we'll say that our dependent observation is approximately this model, which is approximately W1 times the independent observation plus the intercept term. And then, as before, what we do is we calculate each residual error, and that will be the residual error. Now it's a function. For Hooke's law, it was a function of a scalar. Now it's a function of a vector. And that is, so this is a real number that we compute, and it will be the dependent value minus the model and that means it'll be minus W1 times independent observation I minus W2. And when we gather our terms, what we'll see is that that means that our error vector that depends on the parameters that we choose will be the gathered dependent data in the vector C minus our model, and our model is A times W. And here, A will be, we can write this term by term as observation 1, and then to have an intercept we put a constant, and then observation 2, and so on until we've represented all of the observations that are present in our data. And we could write that as a block partitioning as observations in A followed by the ones vector. And we would then solve this using the normal equation. So we can solve this, and the normal equation for this is the same as before. We take A transpose times A and multiply that by the weight vector, and that is A transpose times the dependent observations, and we can then solve this linear equation for the weights W, which are the parameters of our model. Let's visualize the error in a linear regression. Suppose that we have data and that we're modeling these data as being linear, and it could be using Hooke's law, or we may have an intercept term. In either case, we're modeling a line that goes through the data. And in linear regression, the way that we've set up the problem is it will be the difference between the observation, which is its vertical value, and our model, which is arrived at from the horizontal value. So what that means is that what we're doing is calculating what some people refer to as the vertical error. So for each data point, what we're doing is we're calculating the error between the independent observation plus the dependent observation and our model. So that difference between the dependent value and the model is the error, and what we're doing in linear regression is that we're minimizing the sum of the squares of all of these errors, and that geometrically is the same as performing a projection of the vector of dependent data onto the vector space that are spanned by the independent data.